For generations, scientists believed that the universe's earliest history would remain beyond direct observation. The first stellar systems, the earliest galaxies, and the stars that illuminated the cosmos after the Big Bang seemed hidden behind immense distances and the passage of billions of years. Researchers could only build theories and simulations to imagine what those ancient times looked like. That picture changed dramatically with observations from the James Webb Space Telescope. By looking deeper into space than any previous observatory, Webb captured evidence of extremely ancient star clusters that may preserve clues from one of the earliest periods of cosmic history. Rather than appearing as faint, unresolved patches of light, these objects emerged as compact, massive collections of stars surrounding a distant galaxy known as spark. The discovery immediately attracted attention because these clusters appeared to be among the most distant globular clusters ever detected. Globular clusters are dense spherical groups containing hundreds of thousands or even millions of stars bound together by gravity. Unlike many modern stellar populations, these systems are thought to have formed during the earliest stages of galaxy construction, making them valuable records of the young universe. Located roughly 9 billion light-years away, the newly observed clusters offer a glimpse into a period when galaxies were still assembling their structures. Looking at them is equivalent to looking billions of years into the past, observing conditions that existed long before our solar system formed. Their compact nature and enormous stellar populations suggest that they formed rapidly during an era when the cosmos was far different from what we see today. The significance of these clusters extends beyond their distance. Because globular clusters often contain very old stars, astronomers view them as natural archives of cosmic evolution. By studying their properties, researchers can investigate how and when the earliest generations of stars formed and how galaxies accumulated their first major populations of stars. Before Webb became operational, observing globular clusters at such extraordinary distances was nearly impossible. Existing telescopes lacked the sensitivity and resolution needed to analyze these ancient systems in meaningful detail. Webb's advanced instruments have changed that situation, allowing scientists to examine the light emitted by these clusters across multiple wavelengths and estimate their ages, masses, and stellar compositions. This breakthrough provides direct observational evidence from an epoch that previously existed largely within theoretical models. Instead of relying exclusively on computer simulations, astronomers can now compare predictions with actual observations from the distant universe. The story became even more intriguing when researchers examined one of Webb's first high-resolution scientific images. Among countless distant galaxies, one object immediately stood out. Its shape appeared stretched and distorted, unlike the familiar spiral or elliptical forms commonly observed in nearby galaxies. Surrounding this unusual structure were several compact reddish-yellow points of light that appeared almost like sparks scattered around it. Because of this distinctive appearance, the galaxy earned the nickname Spark. At first glance, the surrounding points of light might have seemed insignificant. However, closer analysis revealed that they were physically connected to the galaxy itself rather than being unrelated background objects. Spark was being observed as it existed billions of years ago during a critical chapter in the evolution of galaxies. Scientists soon focused their attention on these compact companions. Detailed examination showed that several of them were not ordinary star-forming regions but genuine globular clusters. 5 of these clusters were identified as exceptionally massive systems containing vast numbers of stars packed into relatively small volumes of space. Their discovery transformed Spark into one of the most valuable targets for studying the early universe. Instead of offering only a distant view of an ancient galaxy, it provided researchers with an opportunity to investigate stellar systems that may preserve information from the dawn of galaxy formation itself. The findings raise profound questions about cosmic history. If these clusters truly represent survivors from the universe's earliest epochs, They could help reveal how the first generations of stars formed, how galaxies assembled their mass, and how the young universe evolved into the complex cosmic landscape observed today. Every new observation from the James Webb Space Telescope continues to push the boundaries of what humanity can see and understand. The globular clusters surrounding Spark are more than distant collections of stars. They are windows into a forgotten era, carrying information across billions of years to tell the story of the universe's earliest chapters. The discovery of the globular clusters surrounding Spark was remarkable on its own, but the deeper implications emerged when astronomers began asking a more fundamental question. How could such massive and organized stellar systems exist so early in cosmic history? According to traditional models, the first galaxies were expected to grow gradually through mergers and continuous star formation. Yet these clusters appeared to suggest that large numbers of stars could form rapidly under the right conditions, creating dense stellar populations far earlier than many scientists anticipated. To understand why this matters, it is important to consider the environment of the young universe. Billions of years ago, galaxies were smaller, richer in gas, and far more dynamic than they are today. Vast clouds of hydrogen and helium drifted through space, providing the raw material needed to create stars. In these turbulent conditions, gravity could gather enormous amounts of matter into compact regions, triggering intense bursts of star formation. Globular clusters may be the surviving evidence of those violent beginnings. Unlike open star clusters, which often disperse over time, globular clusters are held together by powerful gravitational forces. Their dense structures allow them to survive for billions of years, preserving a record of conditions that existed when they first formed. In many ways, they are cosmic fossils, carrying information from an era otherwise inaccessible to direct observation. The clusters observed around Spark appear exceptionally bright for their distance, a characteristic that provides important clues about their nature. Their luminosity suggests enormous stellar populations packed into relatively small regions of space. Some estimates indicate that each cluster may contain millions of stars. Such concentrations imply that star formation occurred with extraordinary efficiency, converting vast reservoirs of gas into stars within relatively short periods of time. For researchers studying the evolution of galaxies, this presents an exciting opportunity. By examining the light emitted from these ancient clusters, scientists can reconstruct aspects of their history. Different stars leave unique signatures in the light they produce. By analyzing these signatures, astronomers can estimate stellar ages, chemical compositions, and formation histories. Each measurement adds another piece to the puzzle of how the earliest structures in the universe emerged. One of the most intriguing possibilities is that these clusters may contain descendants of some of the earliest stellar populations ever created. The very first stars, often referred to as population 3 stars, are believed to have formed from primordial material left behind after the Big Bang. These stars likely differed significantly from modern stars because the universe at that time contained almost none of the heavier elements found today. Although population 3 stars themselves were probably short-lived and disappeared long ago, their existence influenced everything that followed. Through nuclear fusion and explosive deaths, they created the first heavy elements and enriched the surrounding cosmos. Later generations of stars inherited this material, gradually transforming the chemical makeup of galaxies. If the globular clusters near Spark formed shortly after this transition, they could preserve valuable evidence of those early processes. Even indirect clues about their chemical composition may help scientists understand how quickly the universe evolved from its primordial state into one capable of producing complex galaxies, planets, and eventually life. The observations also highlight the extraordinary capabilities of the James Webb Space Telescope. Designed to detect infrared light, Webb can observe objects whose light has been stretched by the expansion of the universe during its journey across billions of years. This ability allows astronomers to study regions of space that were previously beyond reach, effectively turning the telescope into a machine for exploring cosmic history. Every observation collected by Webb contributes to a larger effort to understand humanity's place in the universe. Each distant galaxy, each ancient star cluster, and each faint signal from the depths of space helps reconstruct a timeline stretching back toward the beginning of everything we know. As researchers continue analyzing the Spark galaxy and its surrounding clusters, new questions continue to emerge. Were these clusters common in the young universe, or are they rare survivors from a unique period of cosmic history? Did they form within their host galaxy, or were they created elsewhere and later captured through gravitational interactions? Most importantly, how closely are they connected to the earliest generations of stars that illuminated the darkness after the Big Bang? The answers may take years to uncover. Yet even now, the discovery stands as one of the clearest demonstrations of how rapidly astronomy is advancing. Objects that once existed only in theoretical discussions are now being observed directly, allowing scientists to test ideas that were impossible to verify just a few years ago.